Hi, my name is Rob Andrews, CEO of Helilytics. Thanks for joining us today to talk about field and module reliability and the results of the aerial inspection platform by Helilytics. As a brief overview of this presentation, we're going to talk about introduction to Helilytics and then get into an overview of aerial inspections and some of the most common failure modes we've seen. And then we're going to hop right into a more detailed analysis of some of the data we've collected over the past few years and how that informs some reliability trends we're seeing in the field for PV systems. Then we're going to hop in some conclusions and get on with the rest of the presentations. So as a quick overview of Helilytics, we are an aerial inspection and DC consulting company. We have performed over 60 gigawatts of inspections globally between 5,000 individual sites. And commercially, the main reason for aerial thermography is for the identification of recoverable energy within systems. And to date, we've found over $82 million per year of recoverable energy losses within projects. The data here is from a global data set, though it's primarily focused in North America, Europe, and Australia, where we have our aircraft platform operational. As a brief introduction to aerial inspections are performed from an aerial platform. In our case, we primarily utilize an aircraft platform where we collect high-resolution RGB or visual and infrared imagery. And then that imagery is input into our systems, which identify the location of defects on the site and digitize those into a digital twin model of the project. The camera systems that we use on the aircraft platform is a cooled photonic mid-wave sensor. And some of the data we collect is also from a UAV platform, in which case we're using a long-wave microbolometer. As a quick introduction to some of the main failure modes that we see from systems, first one is balance of systems failures. These are faults which affect a large number of modules, typically related to connector, fuse, or combiner level issues. In this case, this image you're seeing here is a thin film system, and the site was actually hit by a windstorm. So you can see actually in the top area here where a module is dislodged from the site, causing a full string harness to go down. And then down below you can see individual string failures, which are all in the rows down there. Balance systems failures primarily are caused by component failures, non-module component failures, as I said, string fusing and or connectors. And it can also be caused by maintenance-induced damage. So whether it's connections not being remated after a maintenance or combiners being left off, issues like that. Hotspots are what people mostly think about when they think about aerial inspections or thermography, though they typically do have a lower impact on the overall energy yield of projects as compared to some of the other faults we're seeing here. But hotspots are related to three main failure modes. One is going to be from cell damage and cracking caused by shipping, installation, manufacturing, inherent cell design, or external factors like wind or hail damage. The picture you're seeing here, actually, this is caused by shipping damage from projects. So this was where it was shipped improperly, and we saw extensive heating, and in this case, extensive power loss from these modules in the system. We can also see hotspots caused by solder bond heating from improper solder connections, and that can be a precursor to submodule failures, as we'll talk about next. And in addition, it can be caused by cell mismatch, so where we're seeing differences in efficiencies between modules, or between cells, I should say. PID, or potential induced degradation, is probably the most prominent example of this cell mismatch, where the cell degradation caused by the sodium ion diffusion around generally the frame of modules causes the cells to decrease in efficiency and therefore to operate at a higher temperature, so they're visible by thermography. The last failure mode that we'll talk about here, and definitely one that we're going to focus a lot on, is what we call a submodule failure. This is where 1/3 of the module is deactivated. This is a failure mode that is only seen in crystalline modules, but it is quite pervasive in those. And is also the most common warrantable defect that we see on sites. These failures can be caused by a variety of reasons. Cell damage and cracking, just like hotspots. However, if that cell damage becomes too pervasive, it can cause that bypass diode to engage and deactivate 1/3 of the module. It can also be caused by solder bond failure. This is probably one of the most common failure modes we've seen or root causes we've seen for submodule failures. And these solder bond failures or resistive heating will cause solder bonds to fail over time, and that will cause sections or substring to be isolated. And then finally, diode failures. Diode failures is, generally what these are blamed on. However, we see that diode failures is at least not the majority of the root causes here. But diodes can fail in open, which will cause that substring to become isolated from the rest of the string. So we're going to hop now into our field reliability database. And in this database, we're going to see some of the results that we've collected from the aerial inspection platform over the past few years. So to give you a quick sense of what this database encompasses, it's collected from and anonymized from over 39 gigawatts of inspections. That represents 3,500 individual sites and 175 million modules. You can also see a distribution breakout from the data that's in this data set. You're going to see that we're going to be looking at stuff by site age and also by manufacturer. So this gives you a sense of how robust this data set is across some different kind of cuts of this data set. The black bars represent the number of modules, and the orange bar represents the number of sites. So we're going to hop into this, but before we do, we thought it would be good to take a quick refresher on box plots and some basic stats, median and mean. So we're going to use box plots to represent a lot of this data. And just really quickly to orient you on this, the solid line or the horizontal line represents the median in the box plot. This dot represents the mean. The width of the box represents the quartile distance. And so in this case, the top of the box represents the third quartile or the 75th percentile. Means that 75% of sites will have a failure rate less than this, 25% will have a failure rate higher than this. And then the maximum or the whisker, these are called box and whisker plots sometimes, is basically math that is based off of that third quartile amount. And then the individual dots we see above this are outliers that exist above that maximum level. The two stats that we're really going to pay a lot of attention to here are mean and median. And the relationship between the two of those can actually tell us a lot about what's happening within a project and also within a portfolio. So the median it represents the 50th percentile. A site is equally likely to have a failure rate higher or lower than the median. And a median is a good representation of how an individual site will perform or could be expected to perform. However, on the other hand, the mean or the average is the average of all the failure rates we're seeing in a portfolio. And because it represents a full distribution of sites, it is a good representation of the expected performance of a portfolio or a grouping of projects. In the case where we had a perfectly normal Gaussian distribution of failures, we would see that the mean and median would be the same. However, because we're seeing that there's a pretty significant difference between the mean and median, we can see that this is a non-normal distribution, and we'll see that for all of the distributions of failures we're seeing in this presentation. Physically, what this is indicating is that we're seeing a lot of positive outliers, a lot of high power loss outliers, which are causing that mean to deviate from the median. So kind of zooming back into the purpose of this plot, we're looking at what are the average and median power losses we're seeing in sites. So we've broken this down by 3 different categories: distributed generation, which is less than 5 megawatts, small utility 5 to 50, and large utility 50 plus. Some notable differences between large and small utility is that large utility is more likely to be staffed, whereas small utility is generally an unstaffed site. And distributed generation includes sites from kind of community solar size all the way down to rooftop solar. And so those have a lot of unique attributes related to the amount of maintenance they have, as well as inherent module reliability and component reliability. So we can see here that in all cases, the mean is higher than the median, as would be expected, with distributed generation having the highest mean and median, followed by large utility, which is somewhat surprising, to be honest. And then ended by small utility sites. It's also notable here, or important to note, that this is a power loss excluding any large-scale balanced systems issues. So if a whole inverter was off during the inspection, we have excluded that from this data set because that's not representative of the steady state operation of the site. That's just representative of an individual inverter being off at any given time. And we've also filtered this data set so that any total power loss greater than 20% is also excluded from this, because again, that would be a pretty significant outlier from the data set. So we can also look at how this evolves over time. So in this case, we're looking at the evolution of power loss over time, and we're looking at the mean because we're looking at an aggregated portfolio view of for each year. Overall, what we can see up to about 7 years of age, we're seeing a generally increasing trend of failures. And after that, we're seeing a bit more of a variable trend, whereas some of the older sites actually are performing at a better mean power loss than some of the newer ones. And it's also interesting to see that early in the projects, the inverter power losses tend to be higher than as we get later into the year or later into the age of the sites. And this is primarily because for these early sites, they're still having issues with availability control. So what this means when we're seeing a high power loss due to inverters, it means that that inverter was off during the snapshot in time when we were flying over the site. Either it tripped offline during the scan or immediately prior to it. So definitely what we're seeing is that for earlier sites, they're having a bit of a harder time with availability control, keeping inverters on and predicting when they will go offline. And as the sites get older, we're starting to see that gets a little bit easier for the sites, and we're seeing less of these availability issues that are coming in or inverter failures that are coming in. We can also break this out by site size. So, pretty notable here is that for large utility sites, we see actually a decreasing trend over time, where we're seeing, again, that early inverter power loss, which tends to just decrease over time. And then the balance of systems and module losses all are decreasing over time. And this is something that we see kind of playing out in the field, where sites that have a longer operational history are more likely to have better response from field personnel and better tuned data models, which means that they're able to keep that mean power loss closer to that 1% level than kind of spiking up as earlier in the years. For the small utility sites, it looks more steady throughout the time, more evenly balanced, and it doesn't seem to be a significant progression. And where we're seeing the larger amount of this progression of failures over time is in the distributed generation sites, where we're seeing an increase in balance plant and both module level, submodule, and hotspot level failures. We can also slice this another way. So we can look at this by manufacturer. So when we're looking at the manufacturer's failure rate of, in this case, submodule faults, which is just one subcomponent of different reliability issues we could see from a module, we can see that different manufacturers have some pretty distinctive traces over time of failure rates that we're seeing here. And if we dig into this a little bit more, we can kind of pick out 3 different categories of failure rates we're seeing here. So we can see the purple category here, or the bright pink, I suppose, as manufacturers which tend to have a evolution of failure rate over time, but have had known component failures in their history. And what that means is that we can see that there is some spikiness to this trend, where we're seeing that there's an increase and then in some cases a decrease of module failures over time. So this indicates there was a particular component reliability issue at one point in time, which kind of persisted through a production batch of modules. In blue, we can see manufacturers B and E. These represent what we'd consider to be kind of the more normal or predicted long-term failure trends, where we see this increasing rate of failure over time. This is something that seems to be more in line with kind of a standard failure progression expectation, where we're seeing low failures to begin with, and then as we get farther into that failure and reliability, those reliability failures over time, we start to see that increasing with time. And finally, we can see manufacturer C, and in this case, we can see that it has consistent failures with age. And it's actually quite interesting, where we see that it starts even, for newer sites at a relatively at a higher level of failures, but then it stays more consistent throughout the lifetime of those projects. And so that could be because it's related with more inherent damage to the modules during manufacture, but it seems not to be progressive or increasing over time. So thanks so much for your time, and we're looking forward to carrying on the conversation.
Hi everyone, my name is Jenya and I'm with PV Evolution Labs, and today we'll be talking about trends in testing PV modules across different technologies and different manufacturers. First, let's start with a quick introduction to PVEL. We are a test lab that's focused on supporting the downstream side of the market. By downstream, we mean developers, insurers, investors, lenders, anyone taking long-term performance risk on the product. PVEL has been in business for over a decade, and we've tested over 400 unique bill of materials and have generated over 1,500 reports on these. These are all available to our downstream partners at no cost, so please feel free to contact us to become a PVEL downstream partner. Our objective is to help our downstream partners evaluate and qualify modules for your approved vendor lists. Here you see one of our core program, the PV Module Product Qualification Program, or the PQP. It's intended to be a comprehensive testing program to enable effective and efficient qualification and evaluation of potential module suppliers. We support our downstream partners with this program and help manage approved vendor lists and help with equipment selection for different projects. Nowadays, PVEL is evaluating over 100 unique bill of materials every year, which provides a very unique perspective on technology trends, how different technologies are performing, and market share of different global raw material suppliers. We record all these bill of materials and can support our downstream partners with these insights in your module supply agreements. The data I'll be showing today is based on data we've collected from 2018 to 2020, and it's mostly focused on thermal cycling results. So let's get into what we're finding. Over the past 5 years, we've seen a mix of module factory locations supplying the US market and PVEL's PQP. Even with the introduction of tariffs in 2012 and 2014, and then the introduction of new tariffs over the past 4 years, we've continued to see module supply from China, and the market share from China is even increasing over the past 3 years. This chart shows the degradation after 600 thermal cycles across 26 different manufacturers. Each bar is the average of a number of modules, and the different colors represent the region of manufacture. So as you can see, there's a fairly large spread here. There are Chinese manufacturers that perform well and perform not so well, manufacturers from the rest of Asia that similarly perform well and not so well, and from North America as well. So as you can see here, country of production or region of production does not correlate necessarily to the reliability of a module. Similarly, this is the same data as shown on the previous chart with the top 10 module manufacturers by volume highlighted in yellow. We see large volume manufacturers performing well, but of course this is not always the case, and there are many small manufacturers that perform quite well. Over the years, we've seen interesting trends in module technology that I think is representative of what most developers are seeing installed. PERC cell technology, of course, has picked up steam pretty substantially from ALBSF, which was the historical cell technology, starting in 2016 with 20% market share, and in 2020 we actually saw 0 ALBSF for the first time enter PVEL's PQP. Similarly, mono has picked up complete market share in the US market over multi for wafer technology. N-type has always been a small piece of the market, and that seems to be maintaining. I expect this to grow in the near term with all of the IBC, PERT, TOPCon, HIT, or HJT cells picking up market share as more and more high efficiency cells enter the market. The following slides will show a number of box charts that are based on thermal cycling results after 600 thermal cycles across a large number of modules and data points. As you can see on the left here, the modules built with mono cells tend to perform better than multi. Similarly, PERC cells tend to perform better than ALBSF. Of course, this is a good sign since, as we saw in the previous chart, most of the modules entering the US market are mono PERC nowadays. The average value, which is the line that is connecting these X's, is quite a bit lower for multi and ALBSF, and that's because there are a few modules with very poor performance that pulls down the average. The chart on the left here shows how to read a box plot, and we'll be looking at a number of these today. We've seen a large volume of cut cell modules entering the US market. Historically, full cell modules dominated the market, but in the past few years, many of the manufacturers have moved to cutting cells in half. We've even seen some 1/3 cut cells. As we see in the chart here, the modules built with cut cells actually tend to perform better than full cell modules. Of course, there are many individual examples of full cell modules performing quite well. On average, the cut cell modules outperform in thermal cycling. This is probably due to the lower thermomechanical stresses seen in the smaller cell sizes. So the solder joints are simply smaller on cut cell modules than they are on full cell modules. We've seen busbar-based modules really dominate the market for the past 5 years. Originally started out with 2 busbar cells, then 3 busbars, 4 busbars, 5, and eventually 6 busbars. The one similar component these modules had was a flat busbar ribbon. In 2020, we really saw the multi-busbar pick up a substantial amount of market share. These are fundamentally different in that they use a very thin round wire soldered, and typically 9 or 12 round wires soldered to the cells rather than the wide flat busbar ribbon. Here you see busbar performance versus multi-busbar performance. Again, the bus bars are the flat ribbons that are used to interconnect cell to cell, and the MBB or multi-bus bar is these thin round wires as seen in the picture on the right. The wires here are typically around 0.35 millimeters thick or 350 microns, and while it looks extremely thin on this image, it's actually twice the thickness of the cell itself. As you can see here, alignment of these round wires is difficult. The solder joints connecting these round wires to the solder pads are very small, and so this is where you see performance in thermal cycling worse with multi-bus bar on average than with the standard flat bus bar based modules. Another interesting finding is that the thickness of the encapsulant and the thickness of the busbar ribbons matters with thermal cycling performance. When the encapsulant is below about 0.5 millimeter, we start to see slightly worse performance. However, where the correlation is more substantial is the ratio of ribbon thickness to encapsulant thickness. When the busbar ribbon is more than roughly half as thick as the encapsulant, we start to see worse performance in thermal cycling. This is a cartoon or a diagram of how the relative thicknesses here look. So a typical PV cell is about 0.16 to 0.18 millimeters thick. The busbar ribbon is thicker, about 0.2 to 0.4 millimeters thick, and the front encapsulant ranges from about 0.5 millimeter to 0.7 millimeters. Again, when this busbar thickness is more than about half as thick as the encapsulant, we see worse performance in thermal cycling. This is likely because the encapsulant serves as somewhat of a cushion between the glass and the bus bar for thermomechanical fatigue as the module experiences heating and cooling throughout the day and the night. One of the interesting market trends we track is how the market share of the bill of materials, raw material suppliers has evolved. With encapsulants, we've actually seen one very dominant supplier across the years. One supplier has provided more than half of the total encapsulant supplied to the PV industry, and the rest of the market share is spread across over another 20 suppliers. This is different than what we see in the backsheet market, which tends to be much more fragmented. Historically, EVA was the encapsulant of choice for the solar industry. It's fairly stable and pretty low cost. However, we have started to see the introduction of polyolefin or POE encapsulants, especially with glass modules. Typically, historically, we've seen either both EVA or both POE encapsulants in one single module. However, in 2020, we started seeing quite a bit of mixed encapsulants, meaning EVA is used between the cells and the glass, and POE is used between the cells and the backsheet or back glass, typically with a glass construction, so between the cells and the back glass. This is likely because the back surface of a bifacial cell is far more sensitive to PID degradation than the front side, and POE is a better barrier for charge transport and therefore is a better solution, better protection against PID. By putting POE between the back glass and the cell, the module is more protected from backside PID degradation. However, POE is slightly more expensive and has some supply constraints in the market because there's just less POE manufacturing capacity. So we've seen a lot of manufacturers using POE on the back and EVA on the front. This, of course, introduces new chemistries in the module and mixing of chemistries, which could potentially lead to new issues down the road. So, in summary, the technology landscape is evolving rapidly. There is more technological advancement happening in solar PV modules than there has been in probably the past decade or probably the past 20 years. Technical advancements can be positive for PV module reliability, but similarly can be negative for PV module reliability, and we will never get to the point where we have decades of field experience on the modules that are being sold. So lab testing is the best solution for effective qualification of different technologies and different suppliers and an evolving raw material supply landscape. With that, let me close out and thank everybody for your attention today. To all of the developers, insurers, investors, and lenders paying attention, feel free to reach out to us at pvel.com and sign up to become a downstream partner. There's no cost to become a downstream partner, and we will actively support you and share reports with you to help you mitigate risk with PV module supply.
Hello, everyone, and thanks for listening in to what will hopefully be some informative thoughts about navigating the warranty process for failed solar modules. Now, I should say right at the top here that we have been involved in a number of module warranty claims over the years, both as an asset owner and as a third-party operations and maintenance provider. So nothing that you're about to see here is a lesson or detail specific to any one warranty claim process or any one solar module manufacturer. Not looking to pick on anyone, just kind of aggregating some of the lessons that we've learned over the years and hoping for some good discussion in the question and answer session that follows. So just to break down where we'll go today, we will discuss module warranties in general and what is really kind of involved in the warranty in terms of the rights and the responsibilities of the warranty holder. And we'll discuss the decision process between whether and when to file a module warranty claim. Then we will take a look at the terms and conditions that are really in the details of the module warranty agreements. Finally, we'll discuss the documentation that would be prudent to be keeping every day during normal operations, as well as through the claim process. Now, we'll start with module warranties themselves. I think everybody here certainly will have a good understanding of what's involved in a module warranty in general. But then you start to separate the people who've been through a lot of claims when you look at what's typically included in a module warranty versus what is rarely included in a module warranty. And I think this is really important because it helps us understand what our rights are, what our possible recovery is when we look at a module warranty. And I'll go through these common and then more rare features briefly. Obviously a common feature of the module warranty is that it will warrant the output of the module as well as the workmanship of the module. Now it's fairly typical to have both as a feature of the warranty. However, it is, it's typically going to be a pretty long time period for the output warranty. And the warranty will step down as the years go on and the modules have expected degradation. And then there will typically be a shorter term workmanship and material warranty that is meant to capture defects, but expires when presumably those defects would have come to the surface. And it's typical for the warranty to offer either replacement modules or cash compensation, or an option or a combination of the two. When either of those two kind of warrantable criteria is met. And the warranty will also lay out evidence and testing requirements. And this is really important to understand what criteria need to be met and then really what needs to be provided to prove that an event is warrantable. Now, a lot of things that I think folks who purchase solar modules hope or wish will be included in the warranty, but are not as common to be included. It is not as common for things like the cost of the initial diagnosis to be covered, the actual cost of gathering the claim evidence. So oftentimes the warranty will spell out specific pieces of evidence that are required, but it is not typical for the cost of gathering that evidence to be covered. Similarly, the warranty might require some kind of lab testing. And the cost of that testing is, it's usually not fully covered. Sometimes there will be a cost share. Sometimes the cost burden will fall on whoever, quote unquote, loses the claim. But, there again, shipping costs typically are not automatically covered, and that's for lab testing or returning some samples to the manufacturer. Again, there can be cost shares, and often this point is negotiated. Similarly, the labor costs behind removal and reinstallation in terms of removing the bad modules, installing replacement modules is not typically covered. And then lost energy is not typically covered as a result of the claim. So moving on, what we just talked about on the warranties themselves really actually help us think through when we should file a warranty claim, because you actually have to think about all of the features of the warranty and how they stack up. What costs will be incurred during the process by each party, and how do those look when we offset them against the losses that are being incurred as a result of the actual module issue. And it's not always an automatic, yes, we should immediately file a claim, because if there is a slight kind of incremental degradation beyond the expected degradation, and so technically a single module would reach the level of kind of warrantable. This doesn't always mean that the owner of that solar module will end up in the black when it comes to the money they'll have to spend to submit and adjudicate the claim versus what they might recover down the road. And so it's good to just think through all of those inputs and outputs and decide, is this something that makes sense to file right away? Is there a strategy around, hey, we think that based on this failure mode, we'll see a few more, and we should probably wait until it would be more efficient to test all of them at the same time. But on the flip side of that, if you let too much time go by, you're losing more money because of the defect in the module. And you might even let another year tick by, and so the warrantable output curve has gone down again because of expected degradation. So, and of course there are also considerations such as, is the module manufacturer a stable company, or is it a company that might be a little bit shaky, might not have the financial health a few years from now to support warranty claims? And then there is just kind of leaving a condition issue in place. That it's another thing to track. It's another thing to disclose, and versus being able to say that all issues that came up have been addressed. So there are some more qualitative elements to the equation, but it's important to think through it all as one kind of holistic analysis as to whether and when it will make sense to file a claim. Now, moving into the actual warranty terms, this is important. It's really important that before you do anything, you have a full understanding of the contract and the attachments that are applicable, whether it was a purchase agreement that had its own warranty terms, or a purchase order that referenced a kind of blanket set of warranty terms that was applicable at the time of the purchase. It is, I've actually laid out a few example terms that might be specifically defined in a warranty, and what it would look like if they were overlooked or not followed properly. One of those, and it's pretty obvious, is the specific evidence that's required under the claim. It's one of those things where, if you were to just send the module manufacturer an email that said, hey, our modules aren't performing like we think they should, and we went out and took a picture of them, but you actually were supposed to supply electrical testing data, well, get ready for another trip out to the site to provide that data. And, certainly that could have been saved by reading the agreement and making sure that all of the evidence was gathered when on site the first time. There might be, and this is where things can get even more interesting, there might be different processes for different types of failures or different quantities of failures, a single module versus we're seeing underperformance, or we're seeing a defect on hundreds of modules. So it is important to not just kind of glance at the section of the contract that you think would apply to claim filing, but to actually review the whole thing and make sure there's not a whole separate clause somewhere that says, in the event that this type of failure occurs or this number of modules fail, here is an additional piece of evidence that's required, for example. Again, the cost, if this was missed, might be another kind of wasted trip to the site, or it might even be that there could have been a claim that would recover more for the owner if you had read through and made sure that you kind of analyzed all the different types of filings that could be made. And moving on, the claim submission process, it's important. It might be very straightforward, just, hey, send us the information, but it also might be very specific in terms of a specific physical address or email address that a notice must be sent to formally initiate a claim. And you could be wasting time if you didn't follow that process, because you might send the data, but you didn't actually start the clock on the formal claim process. And then finally, just independent testing. This is fairly common in module warranties, that at least once a claim reaches a certain level in terms of number of modules or certain types of failures, there is either a right or an obligation to have the modules tested by a third party, either at a lab or a traveling company that can test the modules on site. And it's important to really know who has this right and who has this obligation, so that you don't get into a claim process and start spending money submitting evidence only to find out that by surprise you also will then have to ship modules to a lab to be tested, and that adds to the cost and the timeline of the claim. So finally, I think another really important layer to this is documentation, and everything that we've talked about so far is going to be made a lot easier if very good records are kept through the life of your solar projects, and very good records are kept through the entire module warranty claim process. And so I've included a few examples here of routine documentation versus warranty claim documentation. Again, this will make it so much more streamlined to submit a claim, to look back in the future and attribute future failures to past warranty claims. All of this, doing it right from the beginning is critical. And so on a routine basis, before you ever have a module warranty claim, it's really important to keep a very granular maintenance history. The first item on the list that I put is a serial number sitemap that actually has module level detail. This can be a point of contention. It's a lot of work, but it will help tremendously if you get into especially larger warranty claims where you have to start tying modules and their locations on site back to specific production runs or purchase orders. So if it's possible, it is very valuable to have that and to keep it updated when modules are switched out as part of maintenance activities. And that's where we go with sort of the log of previously replaced modules. Very important to keep a detailed record, preferably in map format, of where there are new modules that were not part of the original purchase for construction, but were replaced because of a lightning strike or other physical damage that might have happened to the modules, just so that you never get into the kind of confusing back and forth of which PO, which warranty terms apply to which modules on site. And of course, just historized testing records, very important. And then during and after the claim, logging all communications, and that's, you can see the second line here, that includes phone calls. It is very helpful to put a memo to writing after a phone call, and it's great if you can have that kind of sent between the owner of the modules and the manufacturer, just as sort of a meeting minutes that can easily be kind of searched back and, hey, we discussed on the call on this date that we were going to ship the modules, and we did it, for example. And continue logging all of the test results at the module level. And of course, update your serial number map with any results of the warranty claim. All of that is going to help tremendously, and it'll help kind of prevent selective memory in the future, or disputes that might arise from kind of different recollections of how the claim proceeded. So it's a lot of information, again, kind of scratching the surface of all parts of a claim, but I'm now happy to take any questions and answers, and thanks so much for your time and listening.
Hello, my name is Gottschalg, and I would like to invite you to my presentation on quality management best practice guidelines. The guidelines might be a little bit overdoing it here. It's a little bit of a personal thought here, but overall, I would like to point out some of the shortcomings in the industry we have and give you some indications of how I think we could patch that one up. So what I'm going to talk about is, my main point will be that we actually have to spend more money in the short term to save a lot of money in the long term, and I will argue that case. The first part will cover the introduction, which will be on why do we need to bother with this in the first place? And then we move over to what is a general industrial quality cycle and how would what other industries do translate to PV. And finally, I'll conclude with some reasons why this may not be going as well as we hope it should be. And I'll complete with the summary. So quickly to talk about why do we need to spend on quality up front? Sort of in the last 2 years, well, a little bit longer, from 2019 and 2020, there have been 2 publications of NREL, which I found a little bit worrying, I must admit. The short of it is that they analyzed about 20 gigawatts of PV installed in the US, I would guess, and they look at the annual degradation rates. The interesting message is that the median of performance loss is 1%. That means 50% of these systems age faster than 1%, which then translates for me, they age twice as fast as the financial predictions are, which are typically 0.5% per year. What is even more worrying, that they age in average about 1.4%, which is roughly 3 times what the financial warranties require. And for the performance warranties, that is twice as fast a system loss as the module warranty. That doesn't quite equate because this is not necessarily a module loss, this is a system loss. There are some good features in these graphs which they've shown, that there's sometimes up to 5% improvements year to year. That means there is a fair bit of what has gone wrong which is recoverable. However, that means something has gone wrong in the quality management. And this could have been picked up at a much earlier stage. And as I will argue later on, if we pick up faults later in the system's life, they are more expensive to fix. And fixing them up front or avoiding them up front is much, much cheaper. There's also what would appear to be a significant aging. That would mean something has gone wrong in the way we plan our quality. That means we have not really considered any kind of degradation or performance loss. Or alternatively, this is another thing we could say, the quality control has gone wrong. That we have products which enter PV systems. This can be a PV module, but this could be also something boring like a connector or an inverter or things along those lines. But these kind of things are put into a system which cause degradation. So there's a quality issue in PV systems, which I think comes out of this presentation quite clearly. I'm not entirely certain, and I don't really want to speculate on the reasons of the degradation or these factors at all. That's from my point of view. If you look from an end user's point of view, that's neither here nor there. What is important is that actually we have a significant financial risk. And risks are ultimately costs. A risk means that to a certain high likelihood in this case, my system will fail financially, or I need to fix it at a very significant cost as well. And typically this ends up in arguments in who's to blame, and that is always costly. And I'll show you just on the other side some typical reasons where the mechanical integrity maybe wasn't as good as expected. That's a photo I would like to thank Michael Köhl for. I have another photo here which is just a fuse which has gone wrong, but that's really just to illustrate the point that the risks are not necessarily the modules. At the moment, I would contend that the PV industry does not use a holistic quality management approach as we have in other industries, largely because there are costs in the beginning which benefit the end user. And that's the difference. Somebody else has to pay for the benefit of somebody else. There's a mismatch in that. Due to the way the industry is structured and projects happen, we have a highly fragmented approach to quality management and never a holistic view, or hardly ever. I will argue later on, or in a couple of seconds, that we deal with certification as a cost-oriented, not risk-oriented part, which is also very often, unfortunately, linked to quality assurance as a whole. Or if I pass certification, I have a quality product. It's nothing to do with this. The due diligence very often is opinion-based and not driven by quantified risks. And the OMM at the moment is cost-wise on a race to the bottom, and nothing else counts at the moment. So, as I said, there are different people who pay and benefit. That's a problem. But how is that solved in other industries? Why is it better there? So, just as a quick comparison to the BIM, the Building Information Management, which is a concept which is sort of coming into the building industry at the moment. And if we're perfectly honest, PV systems are nothing else but large building projects. The baseline graph here, which is always cited, which in this area is something similar to the famous photovoltaic 3-generation graph, is the McLean graph, where they clearly say that the earlier in the design you implement your risk and quality controls, the cheaper the overall project will be. Initially, a quality first approach will be a bit more expensive, especially in the outline or preliminary design, basic design stage. Maybe even in the executive design stage, you pay a lot more in time and money to get that sorted. But as soon as you come to procurement, that's easier. If you do construction, that could be easier, but certainly if you just run into the EPC warranty period and in the final period, your failures will be much less. Sort of this is a loose translation of the McLean graph into photovoltaics here. We do not consider operational problems in the design phase. This can be something, as I see reasonably often, that the rows are too close to each other that you can't get any shock or anything through it, so maintenance becomes horribly difficult. It could be also some shading issues or so not dealt with. Corrective measures cost a lot more money. That's important to understand. And costs of late-stage design changes are always borne by the asset owner. Even if it is a warranty claim, yes, you might get the product, but still you just have the cost of proving the warranty, you have still installation, etc., etc. So if you want to be profitable, you should avoid these. Very quickly, I show you some things, what I call late-stage design things. On the left time, we had a emergency bonding of tables because they were sinking into the ground and there were structural issues. On the bottom left, we had some interesting grounding issues because of bare cables. On the top right, it's just rotting away brackets, and then we have sort of different wiring adventures. So all these things are avoidable. They cost a lot of money to fix. So generally speaking, why are we so different to other industries? Well, you could always argue that we have a 20-year lifetime, which is more difficult to assess. Yes. On top of it, we actually we earn money with the product, and we do not consider quality control and maintenance as an important task in the industry. So typically we have sort of the 4 stages of reliability in virtually all industries. We have a design reliability, then we have the inherent reliability in all the components we purchase, which we need to verify. We have a reliability at sale, and then finally what happens in the field. So these are different stages. If you translate it to PV very loosely, we would say that the design reliability is purely type approval testing. We do not link it to real operating conditions. We just say it passes type approval. We accept that type approval testing has an inherent permissible failure rate of 30%, but that's a design reliability we have here. We have an inherent reliability, which is the quality control during construction. We do not do any component verification, for example. We do not verify that we have a reliable product. We verify that we have a reliable product design, but not that it has been produced reliably. So there's a big difference here. We also talk the reliability at sale, which I would translate into system commissioning, which we do patchy for larger systems or not at all for small systems. And the field reliability, again, there's a whole story to be told about that. But why do we still, if we just do this approach here, why do we see the degradation factors we've seen earlier? Again, not module specific, it is all we have. And why do we see things like the PA foils, the AAA issue, that foils rot away too early, way too fast? And I think there's an obvious problem here. So why can the problems occur? So we don't plan properly for quality. We just equate type approval with design reliability. As I said, we don't assume realistic mission profiles, and we assume this is fine. We talk about real operating conditions, yeah, for simulation of the power, but not what is, for example, important for the components. Fuses are very often rated at 20 degrees Celsius. Installation values are rated at 20 degrees Celsius very often, not always, but you can look at them. But people don't do that. Electronic component is different. For example, if you look at an electronic component which is rated for a 20-year lifetime in the car industry, that has a use of 4,000 hours. If you go into PV, this is what it does in a year. So there's a huge difference. It's really critical to consider that. Overall, one thing which I also say, SCADA and all the quality control measures are actually planned here without any real consideration of what is happening on site. It's just a cost issue, which we value engineer. The other big point I have is we do not do any quality control. We do not test for lifetime relevant or quality relevant issues. We test for power maybe on a module, but if you look at the component inspection, which is done in other industries and in PV, there's a massive difference there. So there are obvious issues. We have a variety of reports that things have gone wrong. So in terms of a summary, what I've really talked about and what I would like to relay here is that the current state is not adequate. We simply work on costs, and by saving money here, we pay a lot of money later. And the quality management needs to consider the entire lifetime to be efficient. But the most important point from my point of view is that spending money early reduces the life cycle cost and minimizes the risks. With that, I would very much like to thank you very much for your attention, and I hope that all of us have a good conference. Thank you very much.
Thank you, Ralph, for that. I'll invite everybody else, all of the speakers, to turn their cameras and mics on, and we can have a discussion of questions. Last chance for everyone to get your Q&A tab and put your favorite questions. All right, let's see. Do we have everybody? I think so. No, we're missing someone. Ralph. There he is. Okay, the first question is for everyone, which is awesome. Let's kick it off with that. It says, based on your experience, do you think PV system reliability is on average improving or getting worse? And Mike, you appear at the top of my screen, so I'm going to call on you first to address that, but we'll go around.
Sure. Well, I'll actually start by pointing to one of Ralph's comments, which is the desire to save money up front often costs down the road. And so I see a trend in kind of my slice of the world of PV system reliability improving because people are learning that lesson. They have lived through the first few years and they've started to see the cost of saving money. But I would also argue that there are still some more disingenuous players in every sector of the market that are looking for the low bid, that are looking for the low cost of manufacturing. So we definitely still see a sector that is unreliable or that has some serious quality issues.
Thanks. Okay, next up, Ralph, what's your perspective on that? Is PV getting better on average or getting worse?
It's difficult to say because I think PV gets interesting after 5 to 7 years, maybe a little bit longer. So newer systems may be built a little bit better, but what we discover down the road, if it isn't anything which is fast and ugly like PID, then we'll see it later. Most of the foil issues we've seen 7 years in or something like that, and they're not power relevant for another 2 or 3 or 4 years. So I don't know. I think we're saving ourselves to death in many ways. And we have a lot of adventures ahead of us, put it that way.
Thanks. Okay, Rob, as our eyes in the...
Great, yeah, thanks. Yeah, I think, going back to that little stats lesson we did in the thing, I think that average is maybe not the right measure. I would say that median reliability is probably decreasing, I think, or is increasing, that failures in median is getting better, and that overall the industry is recognizing best practices. We have experience with what goes wrong. Now we're able to build things right, and we are seeing that a lot of projects are performing well. But I think, on the other hand, I think that the variance is going to increase. I think that when things start to go wrong, they'll have potential to go wrong in much larger ways. Both because the financial margins on these projects are much smaller for newer projects. So the margin for error is lower, so the financial impact is going to be larger. And also we have this explosion of new technology that's coming out in the field on the module side, and I'm sure Jenya will touch on that. And I think that's where initiatives like these conferences, but also Duramat and all the work that folks like PVEL are doing to try to catch in the net all those things that are going to cause a variance of failure in the future is really, really important. And I think we're getting better at that, but we're going to miss something. We're going to find the next PID, and that's going to cause some pain for some people.
Thanks. Okay, and Jenya, we'll be interested in this too.
Yeah, exactly. I think Rob predicted what I was going to say is I think module reliability, separating module reliability from system reliability, I think on the module side, it's dynamic. I think they were pretty stable for a while. With the introduction of PERC, we saw some systems degrading at very high levels due to LETID. I think a lot of these issues have been resolved now. Of course, now modules are getting bigger, new cell technology is being introduced. So it's a moving target, and sometimes it's worse, sometimes it's better. I think in general, on average, what we're seeing in the lab over the last decade is module prices now are probably 10% of what they were back then, and it hasn't gotten substantially worse. So that's great. Manufacturers are working with substantially less resources to make a reliable module, and the modules are as reliable on average as they used to be. So that, I think, in and of itself is a success.
So I guess next question we've got for Rob, where's the industry with aerial EL imaging?
Yeah, definitely a very interesting field. So I'm going to interpret this as broadly aerial crack detection. And when we're looking at aerial EL, the challenging part is the electro part of that. It certainly is possible to do electroluminescence from the air, and there are some groups that are doing it with drones. You can put a camera on it. You still have to run around and energize each string. And there's some folks that have some innovative ways of doing that, but it still ends up being very expensive. And because you have to energize each string, the time savings of doing that versus doing it from the ground are not significantly different. So that's kind of the state of the art on electroluminescence. Now, broadly, I think that there are some interesting techniques to be looked at for bulk scale crack detection. I think some of the work that's been done by Will Hobbs and Andrew Gabor on fluoroluminescence, for example, I think has some interesting applications in the future, though of course that's limited by cell chemistry. And there's some other technologies that I think are coming up around that. But I would say that it is it's a question of can we? Yes. Should we? Maybe for electroluminescence, anyways.
Yeah, I'll add to that PVAL is actively doing electroluminescence in the field, and we're doing it boots on the ground, going string by string, and it's pretty efficient. We're doing tens of thousands of modules in one, get-go in one project, and it's working. A lot of it is response to force majeure events like wildfires or hurricanes or tornadoes or hailstorms, etc.
Great. So, Rob, while we've got you, there's a question here that says, were these inspections typically done because fields are underperforming, or were they done to see how much of the performance could be improved?
Yeah, absolutely. So, as Jenya was saying, part of the work that we do is incident response. Site gets hit by a hailstorm or a tornado or something, or is just underperforming, and we're dispatched to do that work. That data is not included in this data set. This is the vast majority of the work that we're doing is standard preventative maintenance work. So aerial inspection has progressed from a bit of a science experiment back in 2015 through 18 through to now kind of just a standard operating procedure for PV systems. So the vast majority of the data we're getting is just part of the annual aerial inspections. And so in that data set as well, we did filter out any large deviations. So anything where we're seeing a significant serial defect on the site, we're taking out of that data set as well, because that's not as representative for looking at these long-term trends if there's some of those items. So the interpretation of this data should be that this is generally steady state operations of a normal portfolio.
Our next question is for Jenya. You showed a difference between TC600 degradation for PERC mono and multi. What do you think is actually degrading in TC800 that is a function of wafer and cell type?
So in thermal cycling is, just to describe it real quick, it's going between 85 Celsius and -40 Celsius about 7 times per day on the entire solar panel. So putting it into a oven or environmental chamber and just heating it up and cooling it down and heating it up and cooling it down. And that causes all the different materials to expand and contract. So a PV module is made with glass and silicon and metal and polymers, and these materials expand and contract different amounts when heated and cooled. So the solder joints are soldered onto a cell. That interface is not flexible. That's a hard interface. And so as those interfaces and those materials expand and contract, typically it's the solder joints that we see degrading. Sometimes you see cell cracks propagating from typically small damage that's created in manufacturing. Those that can propagate in thermal cycling. So it's often comes back to metallization and the technique of soldering. What would be different in multi versus mono, or PERC versus ALBSF? It's hard to say. I would say it's probably due to the metallization. There could be active cell properties that are impacted as well to some extent. There could be even encapsulant, things that aren't related to the cell. If encapsulant is under cured, for example, it could continue to cure in the test a little bit. So it's a variety of things, but mostly it's thermomechanical. So it's solder joint related is the primary degradation mode in thermal cycling.
I'm going to jump down here. I see 3 related questions for Mike about like kind of what's covered and what's not covered. So, one of these asks about non-STC performance. Is that covered? Example, low light. Are safety issues generally covered? And then just generally, like what kinds of things might we be unpleasantly surprised about that aren't covered?
Yeah, those are very good questions, and others here might have some thoughts as well. I'll go in order with my perspective, and then I'd love to hear whether a couple of the others here have ideas. Non-STC performance. So I think part of the answer is sort of in the question. You are implying what we've also experienced, that in many, even most cases, there's a requirement for testing at STC, or for really the performance at STC to be key in determining that you're below the output curve. However, we have seen some warranty terms, especially when there was kind of negotiation around the terms, where there is an ability to adjust to STC. That can get a little bit dicey. And then, of course, under the workmanship portion of the warranty, you can often kind of work an angle there where you work with some of the other presenters here, their companies, to think through, well, what might be causing the low light underperformance, and kind of work the angle that, hey, there is a material or workmanship defect. Let's see, the next one is safety fails. So we haven't seen a lot of this specifically being called out in its own section of a warranty, but again, there is often an angle to be explored where you can kind of determine, or at least hypothesize, what workmanship or what material might be leading to it, if you're within that workmanship warranty period. And then unwarrantable events. This can depend on the size of the claim, which is going to increase the incentive of the manufacturer to explore other potential root causes. And so obviously, force majeure, lightning strikes is a pretty common thing that the manufacturer will attempt to point to, and that one or both parties might get into kind of strike maps to adjudicate. And then installation issues is a common route that the manufacturer will explore. Was there any kind of negligence during installation? And then, the last, I would say, big category is issues with other parts of the system, such as grounding, that might lead to module warranty failures that could be blamed. But others here, any thoughts?
Yeah, two quick comments on that. I think one warranty claim reaction I've seen that was unfortunate for the project owner was replacing lost watts. So if 10 megawatts degrades 10%, all those panels are, quote, failed, but you only need to provide 10% of that's the lost watts, so another megawatt. So they got another couple pallets, but they don't have any more land, they don't have any more racking, they don't have any more inverters, and they have 10 megawatts of modules that are degrading at a very accelerated rate. So you got to theoretically repeat that process annually to add more or something. It's just not very effective. The best warranty is obviously the warranty that you never have to use. I think, doing a little bit of, to Ralph's point, doing a little bit of upfront work can help limit a lot of future pain down the road to avoid warranty claim.
Yeah, and maybe just to quickly hop onto that. I think that what we've seen pretty much every time, especially as we're going through larger warranties or warranties where there is a more complex interaction between construction and operations, every warranty claim, there's an art and a science to this. At the end of the day, it's a commercial negotiation. And there is a technical part of it, is putting together a clear technical picture and identification of root causes. And so that's where, as Mike was saying, things like serial numbers and batch identification and detailed testing is helpful for painting that story. And then that informs a commercial negotiation. But I have not seen a warranty claim go through that has not involved a technical piece and a commercial negotiation piece.
Where there's often a lot of finger pointing is cell cracks. Cell cracks in the field are very hard to allocate blame. Some of the field electroluminescence we're doing is actually right post-construction to confirm that there wasn't any rough handling in construction. I think probably a lot of manufacturers should start prioritizing that and then extending warranty confirming that it was installed properly, at least on day one.
Here you have to extend it a little bit further. Also, once you take custody of your cells, whenever you take it, port of import or whatever your contract says, you need to have a check that it has happened before, because otherwise you're left with risk anyway. In a warranty claim, the module manufacturer doesn't care as soon as it can blame it on you one way or another. It doesn't, well, you need to take measures at each step.
Yeah. I think just to pile on the warranty claim thing as well, I see this question from Jim on backsheet degradation. I would say that for us, the biggest wish list item to get onto a warranty would be something related to insulation resistance or wet leakage. We are seeing issues where, you know, wet leakage can cause obviously module damage, but also can cause ground faults in a system, which causes, you know, energy loss in the system directly related to the modules. But it's difficult to transact on if the modules have not had a performance degradation yet. They can cause grounding faults before they have a performance degradation. And so that is a failed module, but it's very difficult to transact on under current warranties. So having some sort of terms in there around wet leakage, I think is not present and important.
That's really surprising that a safety issue like that is difficult to file on, but so it is, I guess. Alrighty, the timer has expired. So at this time, I'd like to thank all of our speakers. Thanks for a great discussion and great talks. And I believe we'll be moving on to the poster awards for the day.
Thanks again.
Guys.
Hello. Now it's our poster winner announcement. Today we are going to give two third place winners. Could you go to the next slide? The first third place winner is given to D-1-2. Santa Maria and Bonetto School. Characterization of electrical parameters of cracked monocrystalline silicon solar cells in photovoltaic modules. Congratulations. And our second third place winner is given to the group D-2-4, Ashna, Catherine, Sona, and Laura, and David and Peter. PV module level solutions for degradation by ionization damage. And place winner is given is Jeffrey Kinsey, solar cell efficiencies under operating spectra. And last, our first place winner is Todd Tuckering and Anuhev Jan on optical characterization of anti-reflection coatings with off-the-shelf RGB cameras. And congrats to all winners. And also, I'd like to thank all poster presenters. Their job, you give very hard job on the judges to place award. And thank you for the excellent work.
Thanks again, everyone. I'm going to put up a slide here really quick, hopefully, that shows the dates of the Sophia workshop. Just wanted to they have now set those dates, and you'll see there it'll be online June 9th from 10th, June 9th to 10th this summer. So please take note of that. I just again want to thank all our poster presenters, the judges. I thought we had some really good talks today. So thanks everyone, and hope to see you bright and early tomorrow.